Okay, we have to another integral from the UNSW integration, be 2019, number 20. We have the integral from -3 to 3, x to the fourth over e to the x plus 1 dx. Okay, first I was tempted to try to use like integration by parts on it, just because we have two things that are pretty easy to deal with. X to the fourth, we could differentiate that and maybe integrate 1 over e to the x plus 1. The thing is, there's actually a very quick way to do this one. I'll do it out a little bit of the longer way, but you could probably do this in just a few seconds, but I want to show how it works. So what I'm going to do on this is we'll do a u substitution for u equal to minus x. Then of course that means x is going to be equal to minus u. Take a derivative, then dx is just minus du. So then when we do this substitution, it's just going to change the signs on everything. Like here, this is going to become 3 to minus 3, plugging in minus u to the fourth, but because the power is even, it's not going to matter, and this is just going to become a plus again, so we don't really have to worry about that. And then in the denominator, we end up with e minus u plus 1 minus du. But then let's just use this minus sign, bring it out front, use it to swap the bounds. So if we do that, this becomes a plus, this becomes a minus. And then all I want to do here is just multiply in e to the u over e to the u, just multiplying 1. The reason I'm doing this is because it's going to kind of flip this denominator around, and it's going to get it to look like this one. When we rewrite this, what's going to happen, we have this becomes u to the fourth, e to the u. This here is going to transform into 1 plus e to the u du. But now let's just do a variable change, switching it back to x, definite integral, so it doesn't matter what variable I choose. So let's change everything to x's. And then let's put some labels on it. So the original integral, I'll call this I. So everything is I. This here is also just I. So now if I add this one and this one, we're going to have two copies of our integral. So we'll call this 2i. Notice we can put them together pretty easily because we've got our bounds are the same, the denominator is the same. So what's going to happen, we're going from -3 to 3. We really just need to add up the numerators. So doing that, what we're going to be left with here is it's going to be, here we'll have this one first, we'll have this x to the 4 plus x to the 4 e to the x dx. But now let's get rid of this 2 in front here, because we just want, our goal is going to be just this I. So if I divide off 2 here, let's multiply by 1/2 here. Then what I can do is, let's factor out an x to the 4th, because we've got that in common here. So this becomes x to the 4 times 1 plus e to the x over 1 plus e to the x. But now we can cancel 1 plus e to the x and 1 plus e to the x, so we're just left integrating x to the 4th, which we can do with power rule. This is why in the beginning I said that we could do this in like 10 seconds, because this actually always works in this case here, where we have bounds are symmetric around 0, an even function in the numerator, and then we have constant base, odd function, and a constant. Actually, this needs to be a 1 right here. And so what that would allow you to do is just basically skip right from here to here in one step. But doing it out, we see how it all works. So what's going to happen is, now this is an even function, so and we're symmetric around 0, so what we can do is change the lower bound to 0 and then pull a 2 out front. So we have that property of even functions that allows us to do that. Just a minor simplification there. And we're just integrating x to the 4th. But 2 times 1/2, that's just 1. Go ahead and integrate. We have just x to the 5 over 5 evaluated from 0 to 3. When you evaluate at 0, that's going to be nothing. You plug in 3. 3 to the 5th is 243. For my final solution of this, we have just 243 over 5. Okay, there you go. Good one today from UNSW 2019. Thanks everyone for watching. Have a good day.